Hello friends, welcome to this YouTube channel. Today we are going to solve one numerical problem on three-phase medium length transmission line. By solving this problem, we shall learn how to determine percentage voltage regulation and efficiency of transmission of a three-phase medium length transmission line using its nominal pi equivalent circuit when values of transmission line parameters and load details are given. A three-phase 50 Hz overhead transmission line has the following distributed parameters. Resistance equals to 28 ohm, inductive reactance equals to 63 ohm, capacitive susceptance equals to 400 micromho. If the load at the receiving end is 75 megavolt ampere at 0.8 power factor lagging with 132 kilovolts between lines, using nominal pi method, we have to determine voltage, current and power factor at the sending end. We also have to compute the percentage voltage regulation and the efficiency of transmission for this load. Let us first write down the given data. Load SL equals to 75 megavolt ampere, that is equal to 75 into 10 to the power 6 volt ampere. Line to line receiving end voltage VR line equals to 132 kilovolts, that is equal to 132 into 10 to the power 3 volts. For star connected system, receiving end voltage per phase VR equals to VR line divided by root 3, that is equal to 132 into 10 to the power 3 divided by root 3, that gives us 76,210 volts. Given load power factor cos phi L equals to 0.8 lagging. Let us now calculate power factor angle. Phi L equals to cos inverse 0.8, that is equal to 36.8699 degree. We know that load SL equals to root 3 times VR line into IL. Therefore, load current IL equals to SL divided by root 3 times VR line. Using values we get 75 into 10 to the power 6 divided by root 3 into 132 into 10 to the power 3. That gives us 328 ampere. Load current may be written in polar form as IL equals to IL at an angle minus phi L, that is equal to 328 ampere at an angle minus 36.8699 degree. This may be written in Cartesian form as 262.4 minus J times 196.8 ampere. Now we shall compute power delivered to the load. PL equals to SL into cos phi L. Using values we get 75 into 0.8, that is equal to 60 megawatts. Given resistance of each conductor R equals to 28 ohm and inductive reactance of each conductor XL equals to 63 ohm. Series impedance per phase of the transmission line Z equals to R plus JXL, that is equal to 28 plus J times 63 ohm. This may be written in polar form as 68.942 ohm at an angle 66.04 degree. Given capacitive susceptance per phase BC equals to 400 micromho, that is equal to 4 into 10 to the power minus 4 mho. Taking receiving end voltage per phase as reference, we can write VR equals to 76,210 volts at an angle 0 degree. Let us now calculate capacitor charging current at the receiving end. ICR equals to VR into half of J times BC. Using values we get 76,210 at an angle 0 degree into half of 4 into 10 to the power minus 4 at an angle 90 degree. That gives us 15.242 ampere at an angle 90 degree. This may be written in Cartesian form as 0 plus J times 15.242 ampere. Now we shall compute current flowing through the series impedance. I equals to IL plus ICR. We have obtained load current IL equals to 262.4 minus J times 196.8 ampere. Therefore, I equals to 262.4 minus J times 181.558 ampere. This may be written in polar form as 319.1 ampere at an angle minus 34.68 degree. Now we shall determine sending end voltage per phase. Vs equals to VR plus I into Z. Using values we get 76,210 at an angle 0 degree plus 319.1 at an angle minus 34.68 degree into 68.942 at an angle 66.04 degree. That gives us 94,995.596 plus J times 11,448.783 volt. This may be written in polar form as 95,683 volts at an angle 6.8721 degree. Now we shall calculate capacitor charging current at the sending end. ICS equals to Vs into half of J times BC. Using values we get 95,683 at an angle 6.8721 degree into half of 4 into 10 to the power minus 4 at an angle 90 degree. That gives us 19.1366 ampere at an angle 96.8721 degree. This may be written in Cartesian form as minus 2.2898 plus J times 18.999 ampere. Now we shall calculate sending end current. Is equals to ICS plus I. Using values we get 260.1102 minus J times 162.559 ampere. This may be written in polar form as 306.73 ampere at an angle minus 32 degree. We have obtained sending end voltage per phase. Vs equals to Vs at an angle delta equals to 95,683 volts at an angle 6.8721 degree, and sending end current Is equals to Is at an angle minus phi 1 equals to 306.73 ampere at an angle minus 32 degree. For star connected system, line to line sending end voltage Vs line equals to root 3 times Vs, that is equal to root 3 into 95,683. That gives us 165.73 into 10 to the power 3 volts or 165.73 kilovolt. Phase difference between Vs and Is, phi s equals to delta plus phi 1. Using values we get 6.8721 degree plus 32 degree, that gives us 38.8721 degree. Let us now calculate sending end power factor. Cos phi s equals to cos of 38.8721 degree, that gives us 0.77855 lagging. Now we shall compute sending end input power. Ps equals to 3 times Vs into Is cos phi s. Using values we get 3 into 95,683 into 306.73 into 0.77855, which is approximately equal to 68.55 into 10 to the power 6 watts or 68.55 megawatt. Let us now determine efficiency of transmission. Eta T equals to PL by PS. We have determined power delivered to the load PL equals to 60 megawatts. Therefore, eta T equals to 60 divided by 68.55, that gives us 0.8753 per unit or 87.53%. Now we shall remove the load from the receiving end and calculate capacitor charging current at the receiving end. ICRO equals to Vs divided by Z minus 2 times Jxc. We have computed sending end voltage per phase. Vs equals to 95,683 volts at an angle 6.8721 degree. Per phase series impedance of the transmission line Z equals to 28 plus J times 63 ohm, and capacitive susceptance per phase BC equals to 4 into 10 to the power minus 4 mho. Let us now calculate capacitive reactance per phase. Xc equals to 1 upon BC, that is equal to 1 upon 4 into 10 to the power minus 4, that gives us 2500 ohm. Now we shall calculate Z minus 2 times Jxc. Using values we get 28 minus J times 4937 ohm. This may be written in polar form as 4937.0794 ohm at an angle minus 89.675 degree. Using values we get ICRO equals to 95,683 at an angle 6.8721 degree divided by 4937.0794 at an angle minus 89.675 degree. That gives us 19.38 ampere at an angle 96.5471 degree. We have obtained capacitive reactance per phase Xc equals to 2500 ohm and no load capacitor charging current at the receiving end ICRO equals to 19.38 ampere at an angle 96.5471 degree. Now we shall determine receiving end voltage per phase on no load. VRO equals to ICRO into minus of 2 times Jxc. Using values we get 19.38 at an angle 96.5471 degree into 5000 at an angle minus 90 degree. That gives us 96,000 900 volts at an angle 6.5471 degree. Let us now determine voltage regulation, that is equal to VRO minus VR divided by VR. We have computed receiving end voltage per phase on load VR equals to 76,210 volts. Therefore, voltage regulation equals to 96,900 minus 76,210 divided by 76,210. That gives us 0.2715 per unit or 27.15%. So today we have solved one numerical problem on three-phase medium length transmission line. By solving this problem, we have learned how to compute voltage regulation and efficiency of transmission of a three-phase medium length transmission line using its nominal pi equivalent circuit when load details and values of transmission line parameters are given. Hope this lecture has been useful for you. If you have any suggestion or question, please drop it in the comment section below. If you have liked this video, give it a thumbs up and share it with your friends. Thank you.